10-10-17. So this moves us to John Dalton, our English school teacher. And Dalton was a school teacher, but he was also just an academic in general. So, you know, what were called schoolmasters at the time were probably a little bit more like college professors in some ways, in that if they were interested in the sciences, they were probably doing research. And Dalton was. He's actually the one who proposed that law of definite proportions that we did not get to explore because it requires nitric acid, and we just don't keep that stuff around. Dalton looked at the observations that had been made, at the laws that had been proposed. And just to give you a sense of the difference between a law and a theory, and this would have been a hypothesis at one point, laws don't explain anything. Laws just describe. So the law of gravitational attraction is one that you interact with on a regular basis. Every time you drop something, you're interacting with the law. You know, the effects of the law of gravitational attraction. Do we know why objects with mass are attracted to one another? No, we don't. We can't explain it. We really don't know. We know that they are. We can describe it mathematically. We can predict their behavior based on it. We don't understand why. Laws don't explain. So, law of definite proportions, law of conservation of mass, law of multiple proportions. These don't explain why in a sealed vessel the products and reactants in a reaction weigh the same. It doesn't explain why we get small whole number ratios for an element in a compound. It doesn't explain any of that. It doesn't explain a thing. And I have up here somewhere, where is it? I'm not a theory. I don't have to explain myself to you. One of my favorite former students' chemistry cartoons. Laws don't explain. They only describe. So Dalton comes along. He takes a look at these three laws: conservation of mass, definite proportions, multiple proportions. And he attempts to explain them, to take the observations from many scientists and explain them somehow. And what he proposes, it's initially a hypothesis, which is, remember, just a working explanation. It's the best we know. Now, because for the most part his hypothesis stood the test of time, we now talk about it as Dalton's atomic theory. He says that everything is made up of these little tiny pieces, atoms. And he borrows this word from Democritus. He uses an anglicized or Englishized version of atomos, that Greek word that meant indivisible. He says there are little tiny pieces that make up everything. And that atoms of any element, so atoms of, and he has just named this new element oxygen. At this point they know of sulfur, gold, lead, iron. They know of some elements. They're working on hydrogen. Any element, any atom of any element is identical to all other atoms of that element. So every gold atom is identical, every carbon atom is identical, every oxygen atom is identical. And he says that you can't create or destroy an atom. They just exist. And you can't divide them. Okay, he has two more things to say. He also says that what you're really seeing when you have a compound is that you have atoms of different elements combining in little whole number ratios. 1 to 2, 2 to 3, 3 to 5, 2 to 3. And that's what forms compounds. And that all a chemical reaction is trading dance partners. That in chemical reactions, atoms just combined in different ways or are separated or are rearranged. And this is actually fairly radical. So I forgot to hit record. Modern atomic theory largely is still based on Dalton. There have been a few modifications. The whole idea that we can't divide atoms, well, we know that we can. There are subatomic particles, and they can be divided. I mean, you can split an atom. It ceases to be an atom of whatever it was to start with then. So, but we didn't know that yet. And the other one is isotopes. Dalton was unaware of the presence of isotopes. He assumed that all atoms of any element had the same mass, and we know that's not true. There are different isotopes, which we'll talk about a little bit later, of elements. But what's astounding is really that, you know, this was proposed initially in 1808, and for the most part, it still underlies most of what we know about atoms. That's kind of cool. Good job, John Dalton. So a couple years ago, I saw this as an illustration, and I liked it. I tried to figure out a way to do this as sort of setting up my teaching year for chemistry, and I haven't figured it out yet. Maybe next year they'll be my guinea pigs. I don't know. But if we think now about, so let's just actually draw a picture of what Dalton's atom looks like. What is Dalton proposing here? Well, this is basically what Dalton's proposing. This is not really exciting, Moser. I gotta tell you. I'm not engrossed. That's supposed to look real three-dimensional. It doesn't. Dalton's proposing this sort of monolithic little tiny block, this single thing, nothing below that level. That is Dalton's atom. He's not proposing all the crazy stuff that the Greek philosophers talked about with different shapes and hooks and, you know, hooks and eyes and practically Velcro. No. But it's this chunk of matter, this indivisible piece of matter. That's the foundation of Dalton's atomic theory. Okay, well, good. But, you know, we should talk about science as a parlor trick. This thing right here is called a cathode ray tube. Who here knows what a tube television is? Who here actually has, okay. Oh, thank God. There will come a day when none of my students will know what a big fat television is with a tube in it. And I used to get a lot of pictures in this project of cathode ray tube, and they would show me a television. That's not the cathode ray tube we're talking about. So this is a primitive cathode ray tube. This did give rise to what we then know as CRT televisions and CRT computer monitors. They're all flat screen now. But these things are cool. Great party trick. And, you know, we talked about how in the 1700s, it's basically nobility who has the sort of latitude to play, to experiment, to do science because they have the money and they have the freedom to do that. They're not tied down to finding other ways to survive. By the time we get into the 19th century, there's a lot of what I will call science as a parlor trick. So you have things like the Royal Academy of the Sciences in London. You have these European and American as well, but the things like the Royal Academies tend to be more central to Europe. These sort of scientific organizations, but they depend on funding. They depend on the nobility largely. So you have, you know, demonstrations of interesting things in science, cathode ray tubes, condensing gases, doing all sorts of tricks. That it's kind of like a magic show, except it's science. That things that will make an audience full of people who don't know much about science go, ooh. And remember, this is existing in a world that's largely without, well, it's a world that's not electrified. It's a world that's not electrified. So this is kind of magical. Basically, you take this glass tube, you suck most of the gases out of it, you vacate most of the air, you create a vacuum, and then while it's in that vacuum state, you crimp the ends shut with a piece of wire sticking in each end. So what you have is a low pressure gas tube, and, well, that's interesting. Most often, these were filled with something like hydrogen. They were filled with some inert gas, some gas that wouldn't catch fire. And then you run current through it. You hook up a source of electricity. They had electricity. They were playing with electricity a lot. They thought it was interesting, but they didn't really understand what it was necessarily. Well, what they knew was that when you took this, and this is actually in this form, it's called a Crookes tube, this cathode ray tube, when you took it and ran current through it, if there was a little screen that had phosphorus, which glows on the end, you would get this beautiful streak of light inside the tube. It's like magic. But it's science. But they didn't understand what it was. They didn't know what they were looking at. So lots of people did this. This was this great parlor trick. It took well, actually, here, let me show you the video first. So Thompson sees this beam in there, and he does exactly what was just shown there. He takes a magnet, and he takes the negative end of a magnet, and that beam bends away from it. That beam is repelled by the negative end of the magnet. It's attracted by the positive end of the magnet, and we know that like charges do what? Repel, while opposite charges attract. So what we now know is that that beam is in fact somehow, we still don't know how, we still don't know what it is, but that beam is negatively charged. Now there were a few other experiments that Thompson did with this beam. Who here has seen a water wheel at a mill? You gone down to the park? Have you seen a windmill? Okay. Windmills! Drive down the turnpike, head towards Breezewood, head for the south anywhere, and you get to the Laurel Highlands and you start to see windmills on the ridges. What moves the windmills? Wind. Clever bunch you are. I'm telling you, best and brightest. Yes, the wind! What's the wind? I don't know. I never really thought about that before. This is kind of like a deep question for over coffee late at night. I don't know. What is wind? Moving air. What is air? No, seriously, what's air? Well, it's 20-some% oxygen, 72% nitrogen. What is it? Some percent carbon dioxide, methane, argon, all kinds of weird little extras. It's particles. Okay, everybody, take your hand and go. Can you feel things hitting your face? What's hitting your face? Air. Why can you feel it? Why can you feel it? Now I'm just having fun. Why can you feel it? Because it's actually a physical thing hitting your face. Ow, that wasn't fun. Okay, so what Thompson did was he took a little tiny thing, looked a little bit like this. Let me make my quick mock-up. Very rudimentary paddle wheel. Well, what Thompson does is he takes that little paddle wheel, and I've drawn it here from a side view, and he builds a Crookes tube, because at this point in the history of science, you don't really order scientific supplies from a catalog, you make them yourself. So if you're experimenting with a Crookes tube, you know how to bend glass, you know how to put in electrodes, you know how to create a vacuum chamber, because you can't go buy a Crookes tube from the science supply catalog the way I can. Why don't I have a Crookes tube in this room? This is ridiculous. So anyway, he built a Crookes tube with a little tiny paddle wheel on a sort of track in there. And then he fires it up, and you know what happens? Whoa, the little paddle wheel, she rotates. Whoa. She goes back and forth like a paddle wheel on a boat. I'm doing a very bad job showing that, but it's the best I can do. And now it fell off, but ignore that. It moves! The little tiny paddle wheel gets hit, like flick, 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 by the cool green line, flick, 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 and it moves. What does it mean that you can feel the wind on your face? Come on, everybody do it with me, it's fun. Thank you for playing along. What does it mean that you can feel something, that you actually feel it? That's actually matter hitting you. But that's an actual physical piece of matter. This is not just some sort of weird energy. This line is made up of actual chunks. In order for one thing to strike another and move it, it's got to have mass. They knew this already. This was established physics. This is really basic physics too. But in order for something to get hit and moved, it's got to have mass. So now we know that not only is this negatively charged, but made of particles. Made of particles, made of actual things that have mass. So he's come up with two things. This line, this beautiful glowing green line that makes a great party trick, has mass and has a negative charge. Based on that, Thomson in 1897 proposes that cathode rays are actually tiny negatively charged particles called electrons. And he thinks that these particles are present in the atoms of what gases remain in the tube. So he has to figure out a way to fit these into the model of the atom, because remember, at this point, we're still working with Dalton's atom, which is just this sort of monolithic lump. And what he says is that there are little tiny pieces of negative charge that are scattered throughout it. Now, Americans don't know what the heck a plum pudding is. It's a British thing. We'll talk about it tomorrow. Have a good day.